I am very thankful to all the organizing committee for the following functions. My title is on controllability and observability of the distributed fraction continuous system with the regular pencil. Actually, the notion for the control theory are very long. In 1960, Salman started to develop the necessary and sufficient criteria about the controllability and observability, obtain some rank conditions for the following system. And obtain rank criteria about the system 1, the rank of B, A, B and so on is L. Here A, B and C and D are constant matrices. This is the classical case where the derivative is simply the with respect to T first derivative of this one to the notation. The things are going to generalize in some sense that the derivative are changed in the fractional case. Here we are considering the following system. Here the d alpha is the Caputo derivative in the fractional sense. Alpha is between 0 and 1. X is our state vector, U is our input, A, B and C, D are constant matrices. The generalization is as follows. Here E is our additional matrix in the sense that E can be identity. If E is an identity matrix, then we obtain the classical one, which Kalman obtained rank conditions. But interesting case is that if E determinant of E is 0, then the thing will be changed. Let's see what happened. And we are assuming that the pencil is a regular mean. The determinant is non-zero for some f belongs to complex plane, and the determinant of E is non-zero, then we can obtain the solution by considering that Laplace transformation method and obtain the following state transition matrix. Here gamma is the notation for the Euler gamma function, and if 2 represent the solution for the following case if E determinant of E is non-zero. This is non-result actually, and this is the definition of Dirac-Leffler function for 2 parameters for particular choices of alpha and beta. Alpha, beta are usually we take in 0 and 1, between 0 and 1, and this is the relation between the state transition matrix and Dirac-Leffler function. And this the next result is about the derivative. If we take the Caputo derivative of state vector state matrix, then it satisfies the following relation. And the next is about the inverse. Dresian obtained this following definition to change the definition of inverse in the following sense. Actually, he didn't consider that the product is equal to identity. If it satisfies the following three conditions, it will. We say that ED is the Dresian inverse for the matrix E, and these are 3 steps. We can compute ED as follows. First, we have to find 2 matrices with the following dimension satisfying the rank condition, and product is equal to E, and we can compute this one because it will be invertible. And then the last one is about the ED is defined as follows. It is the Dresian inverse, and if we have the case that E determinant of E is non-zero, then we can the inverse will be classical one. uh, as in the analysis in the classical case. And in a simple example, if we can consider in this one, it is easy to see that the determinant is non-zero and the rank of E square is equal to E. It means that index to the matrix is 1. By using the same procedure, we can compute ED is this matrix, and we can verify that this ED satisfies the condition of definition. Next, we change the system 1 by using the regular pencil condition. We can compute EC minus A inverse to the equation 1 and obtain the system 6. And this is the solution for the system 6 by using the Drazen inverse matrix. Here, this is the generalization of transition state matrix, and it is just like the evaluation of constant formula for the system 6. Because we know that we can obtain results of controllability and observability in all the sense, in analytical sense, in geometrical sense. Somebody is working for the geometrical conditions, and some obtain result for the analytical conditions. And we obtain result in analytical sense, and especially in the rank conditions. This is the definition of controllability. We know the definition is well known, and we consider the case that determinant is not equal to 0, and define this gradient matrix, controllable gradient matrix, by using the state transition matrix. And we say that the system 1 is controllable. It is our necessary and sufficient criteria. This is new result about the system 1 when determinant of E is non-zero. The system 1 is controllable on interval, on finite bounded interval, if and only if the matrix WC is non-singular. And you can there is also, you can see that it is again symmetric. WC is symmetric matrix and positive definite if it is non-singular. And if the determinant of E is equal to 0, then we try to obtain the same type of gradient matrix and obtain the condition necessary and sufficient criteria about the controllability of the system 6. And it is an interesting one. We obtain the following gradient matrix is non-singular, then the system 6 is controllable on the interval 0 to TF. TF is our final point, and this is rank condition, just like the Kalman obtained in 1960, but this is generalization in the sense that we are considering here matrix E instead of identity 1 here, and this determinant of E is equal to 0. And next is about the observability. Systems are said to be observable on the interval if and only if the state is uniquely determined by the corresponding system input and system output. Again, we have two cases. If the determinant of E is non-zero, we have the following gradient matrix. Here we are involving, instead of B, here C, and transition matrix. System is observable if the matrix is non-singular. And the next result with the condition that if determinant of E is non-zero, then the rank condition is as follows. It is again the necessary and sufficient criteria. And next result is about the determinant of E is equal to 0. System is observable if the following gradient matrix is non-singular. And the last one is about the system is observable on the interval if and only if the rank of the following matrix is n. And these are references definition can be seen here in this book. The die Tagloric is a very famous mathematician and working on the fractional system, especially in the circuits in the electrical engineering. We obtain many results. There are some books, and the last is we use some ideas from these references and obtain some results by using some definitions. That's all. Thank you.
Gracias.